Good morning. My name is Andrea Piccolo and I am an early-stage researcher in the framework of the Marie Sklodowska-Curie European Training Network Zephyr. I come from Naples, in the southern part of Italy, where I've studied aerospace engineering at University Federico II, and now I am pursuing my PhD at Delft University of Technology in the Netherlands in collaboration with Siemens Gamesa Renewable Energy. The topic of my PhD concerns the analysis of the effects of inflow conditions on the source noise of large onshore wind turbines. In fact, the flow the turbine interacts with can be disturbed because of the presence of complex terrain, because of the presence of trees or buildings in case of installation close to urban environments, and also because of upwind turbines in case of wind farms. This turbulent flow can significantly affect the wind turbine performances, and in my case, the goal is to study the interaction of this turbulence with the leading edge of the blade. This flow-induced noise source is called leading edge noise or also inflow turbulence noise. This mechanism is usually accounted for in industrial application through semi-empirical or analytical methods that relate the far-field noise to the upstream flow characteristics through a propagation model describing the interaction and the response of the airfoil to the perturbation. These models will therefore have a low computational cost with respect to numerical simulation, but their accuracy will also depend on the physical modeling of the noise generation mechanism they are based upon. For example, these models prove to be inaccurate in case of thick airfoils, and this discrepancy has been attributed to the distortion undergone by turbulence in the interaction with a non-thin body. The idea in my PhD is to include this phenomenon into low-fidelity methods by modifying the input modeling the upstream flow conditions, with the purpose of relating the far-field noise to the characteristics of the flow in the distorted region. These characteristics can be calculated starting from the upstream undisturbed part of the flow field by applying the so-called rapid distortion theory, developed exactly to analytically model the distortion of turbulence interacting with thick or bluff bodies. The objectives of this PhD can be therefore summed up in these 3 points. The first point, of course, is to acquire a thorough physical understanding of turbulence distortion and its impact on the noise generation mechanisms. This will allow to enhance the noise prediction methods and also to develop noise mitigation strategies. These results that represent the starting point for significant steps forward at different levels can lead, as regards the industrial application, to the achievement of a computationally and physically efficient noise prediction tool, and therefore to a general optimization of the wind turbine design process and consequent performances. Thank you very much for your attention.